right, yeah, let us start. So last time I wanted to just give a, I don't know, a little bit better concluding argument for the proof of most of rigidity. So let me write that the end of proof of the Mostow rigidity theorem. Mostow rigidity theorem. So let me remind what was the picture. The picture was that we had, okay, essentially it was that we had an isomorphism between fundamental groups, and it was a long chain of steps, which ended up with the following map F, which is from HD to HD pseudo-isometry, such that its restriction on the boundary, such that df from the boundary is a homeomorphism, which is quasi-conformal and differentiable almost everywhere. So such that this is a quasi-conformal, differentiable almost everywhere, right? And this implies that the differential of this boundary map is also quasi-conformal. Is also quasi-conformal. So we analyzed this differential of the quasi-conformal map. So we have the following, right? We have that map. So this is my boundary of the hyperbolic space. So this is sphere. Okay, let it be SD-1, right? So this is my map, boundary map F. Then the differential sends tangent planes to tangent planes. And the idea was that I take a circle in the so I take the circle here, and my differential of the boundary map sends tangent space to the tangent space. So I will get something here. But what is important that here I have an ellipsoid. And so we discussed this eccentricity function Ex, eccentricity, which was the product of lengths of axis of this ellipsoid. And ergodicity implies that this eccentricity is a constant function, right? So Moore ergodicity gives us that gamma acts ergodically on SD-1. So this is an ergodic action. And then this implies that E is almost everywhere. Sorry, it's constant. C almost everywhere. Then I wanted to do something with the case when C is not equal to 1. So assume C is not equal to 1. And I also assume that D is equal to 3 for simplicity. Just to show geometrically, okay, like to use elementary geometry ideas staying behind this. So in this case, we have just a two-dimensional. And so I started writing the following. I started doing this. I assume now that this is my sphere S2. And for every point, right, X, so what I have this axis of this ellipsoid, right? So I kind of have this vector. Okay. In this case, it's just a vector field, right? I have a vector field. So for every point X, I have this axis. I don't know how can I denote this. Okay, let it be just, I don't know, Lx, right? And then if I choose another point Y, then I have the associated vector Ly, right? And I want to find this angle between these two vectors after the parallel transport, right? So using the parallel translation along this unique geodesic, I can move this vector from, well, it doesn't matter. I can move from X to Y, right? And then I obtain the image. So, okay, it should be something like that, right? So this vector is, what is it? This, I don't know, how can I denote? Let me denote it as from X to Y. So parallel transport from X to Y. And I apply, maybe the notation is not good, so probably it's better to X to Y. And I submit here, plug in here L of X, right? So I have the angle between these two vectors, and this angle was basically encoded by the functions I was trying to write. Those functions were just scalar products between my vectors, right, and its images under parallel transport. The scalar product, you basically can find the cosine of angle between this. So my functions Pij from the previous lecture they define, in fact, the angle between, like, such angles, right? Such angles I know I can say that the angle alpha xy is angle between Ly and the image of Lx under this parallel transport, right? So they in fact define such angles, and I will just write, I don't know, alpha ij. And then the idea is that if I have 3 points, then I can just make a loop, right? I can walk around this triangle and come back. And the angle I will obtain, so my this moves somewhere here, then here, then here, and I will obtain probably another. Okay, I don't have enough colors, but what I mean is that for 3 points, x, y, z, we can define the angle, and I can enumerate it as alpha x, y, z, which is going to be an angle between Lx, right, and then 3 parallel transport. So it should be Pyx, then Py, then Pxz of Lx, right? And again, this angle should be constant almost everywhere. So, okay, I need to be a bit more careful here. So one can show, technically what I need to show, that in fact, gamma acts ergodically on, so this is ergodic on the product of, okay, SD minus 1 times SD minus 1, SD minus 1, SD minus 1 minus diagonal, and the action is diagonal. So diagonal action is ergodic. Well, it just follows from ergodicity there. And this implies that alpha x, y, z is also constant almost everywhere, since these are just functions from, right? Well, basically just look here, the scalar product I defined here, it was a function from the product of two SDs to R, right? It was.
Should probably be threefold product minus the diagonal. Because you want 3 coordinates 6, y, z.
No, I still want 2, I think. It's just the point is that so I still work with pairs of vectors always, no? Right?
Yeah, but
I think that's enough.
the vectors are drawn from the tangent space, right?
Yeah. I'm not sure. Generally, okay, it still sounds to me like 2 vectors. Okay, the 2 components is enough, but okay, I will think about it. But yes, okay. So ergodicity indeed implies that this is constant almost everywhere. But then you can check that this angle actually, on the other hand, this angle equals the area of this spherical triangle. On the other hand, one can notice that alpha x, y, z equals the area of the spherical triangle, well, spanned by x, y, z, right? I just suggest you to draw a picture when you take the triangle with angles pi over 2, pi over 2, pi over 2, and you will see that this is exactly what was going on there. You will get the angle between them again, pi over 2, and this will be just counted. So, well, yeah, you will see that this is a triangle. So it's not a constant function, right? Not a constant. And contradiction. Oops. Not almost everywhere constant. This is one way. So another way is to notice. I think that when D is greater, one can probably find a subsphere of dimension 2 and project. But probably this requires some work to show that you can always find a subsphere such that you can project and then apply this argument. So I will write here. Probably one can find a good subsphere of dimension 2. And then proceed. But there is a bit, so one can also look at this a bit differently. One can start with this axis, and since again, we use that this axis, okay, what we use that, in fact, gamma acts on the boundary by by conformal transformations, right? That's why all these angles do not change. So we get this invariant, gamma invariant field, right? So one can also try to then just rotate this axis and to see that if you rotate at any angle, you also leave it, you will leave this gamma field, you will leave this field gamma invariant, and then it will give you something something like a cone of definitely not non-zero measure and definitely not of the full measure, and then this entire cone. So you will try to just like cover all this here with different angles, and then you do it in each tangent space, right? And this thing is going to be still gamma invariant. Then you use ergodicity to say that, okay, I have a gamma invariant something of something non-trivial, which definitely has non-zero measure and which is not of the full measure, but is gamma invariant. Contradiction to ergodicity again. There is probably another approach to this, a bit more, I don't know, just group theoretic. What I was trying to do is that this, so approach 1, okay, yeah, I do not want to, I just wanted to mention this since apparently this approach is already a little bit more modern, but I will just roughly give the idea. So if, again, if C is not equal to 1, if this is eccentricity, we have a sub-bundle, okay, gamma invariant subbundle TU, right, in PD as D minus 1. And this implies, this should imply that there is a gamma equivariant map, sometimes called just a gamma map, from G P to G sub G U, right, where this is the stabilizer of some certain k-dimensional plane. So this GU is a subgroup of P, but in fact it contains the diagonal subgroup A plus from the Cartan decomposition, but it doesn't matter right now. So what matters is this just also non-compact closed subgroup. So yeah, so you see like a very, one can try to do some like stupid maps, like take GP to G times GU, but this group is larger, so this map generally is not well defined. So your map will probably look something like G, like coset GP is mapped to something like, I don't know, f of G, G, right? If this group is, yeah, since the problem is that this group is larger, so generally you can, I mean, sometimes you can just define it as GP to G times G sub U, but then the point is that you can have, you may have a problem that you have two elements. Well, basically you have one coset that splits into different cosets in the image, right? So generally this would look like that, and you need to show that there is no such gamma map. But you probably can say that you have no such gamma maps. Okay, so this can be reformulated as no gamma maps from G to G, GU, sorry, G mod GU. And eventually this would lead to, so let me just write. So the letter would lead to a map from G mod gamma to G mod GU. Okay, to P invariant map. P invariant map from G mod gamma to G. And this would give a probability measure. This would give a probability measure here invariant and well, basically supported in the fixed points of P, but this would also contradict ergodicity, since, yeah, here everything is, on the right, everything is gamma invariant. And to a probability measure, whose support is contained in P fixed points. And also contradiction with ergodicity. So this is basically the way I tried to do it last time. So it would come from Gmod gamma. So we have a,
So it would live on G.
yeah, it would live on Gmod G, right? Probability measure on Gmod G, yeah. The probability measure. Right here. So we have probability measure here, since it's just hard measure, right? And then we push forward it to then, and this contradicts ergodicity again. Yeah. So in fact, as I remember, when the original proof of Mostov probably was more like along these lines, but the only point that Moore ergodicity theorem was proved a bit later. What Mostov proved is ergodicity of so what Mostov used the ergodicity of geodesic flows, and from ergodicity of geodesic flows, Mostov proved ergodicity of gamma action on the product of boundaries, and then probably again this argument, but again it's in higher dimensions is more complicated. So I think that was the original approach. Okay, yeah, I'm really running out of time, so let me start arithmeticity, since this is also a pretty nice topic. It is also sometimes technically complicated, but so now arithmetic properties of discrete groups. So in fact, we already discussed a couple of things related to arithmeticity. So we had some subgroups arithmetically defined, right? In particular, PSL to Z. It is a group which is defined using just integer numbers. So a general definition of arithmetic lattices. Like, okay, I think I will give you first a general definition of arithmetic lattices. Then we will discuss even a bit broader context of just lattices and their joint trace fields. This is quite, yeah, this is quite important. And then, okay, let me think what is the best. Okay, I think I will do it this way. Okay, so just by definition, if G, okay, let it be, I think, a semi-simple duality group without compact factors. Oh, okay, let G be a semi-simple group without compact factors. So basically, it means that it can be, G can be, I don't know, something like SLN R, SO, and 1, or it can be product of, okay, I'm a little bit sketchy here, but it's connected component, or it, okay, it is isogenous, it is so-called isogenous to the product of some simple components, but none of this being compactly grouped. Okay, so generally, well, in fact, the notion of isogeny is something close to commensurability for in some senses, yeah, it's in the spirit of commensurability of discrete subgroups, meaning that basically it's up to like finite quotients. Okay, so and let gamma be a subgroup. So a subgroup gamma is called an arithmetic. So a subgroup gamma in G is an arithmetic. Okay, it's called arithmetic. If there exists the following. If there exists a rational algebraic group okay, semi-simple group, I don't know, let me denote it H and this surjective morphism from the connected component of H of R to, I don't know, let me denote it by, okay, from H of R connected component to G. Okay, just to G with compact kernel. Such that gamma is commensurable with the image of integer points of H. Such that gamma is commensurable with the image of integer points of H. All right, so this is a general definition. And in the very, like, in a broad, in this like broad setting, there is the theorem of Borel and Harishchandra. Is a very fundamental paper published in the Annals of Mathematics in 1962, states that gamma, or any arithmetic lattice gamma, any arithmetic group gamma is a lattice. So any such arithmetic gamma is a lattice in the Lie group G. So these groups are lattices, which means that they admit a finite hard measure on the quotient, or in the corresponding symmetric space G mod K, they act properly discontinuously by isometries with finite volume fundamental domain, right? So these are very nice. Yeah, and I will highlight arithmeticity here. Okay, so we already see many such examples. Yeah.
H Z always connected because like Y is from connected.
So B.
Ah,
So your surjective morphism is from connected component.
yeah, it should be. Yeah, it should be to the connected component. Yeah. If it is not connected, we just say that the. Okay. Yeah, that's a good question. So and if gamma, if G is not connected, then we say that gamma is arithmetic if its intersection with G's if this connected component is well, is an arithmetic lattice in G. Okay. So let me modify this a little bit. So let G be a connected, right? Connected. Yeah. I will remove this And then I will say that for non-connected, we define it as the intersection is connected. So for non-connected, G gamma is arithmetic if its intersection is connected, is arithmetic in the connected component of G. Okay. All right. So let me. Yeah, I have a few more minutes to give just to mention examples and okay, so as an example, I can just take any classical if H is any classical, say, simple K group, then gamma, which is H of Z, is a lattice in the Lie group G, which is H of R, right? And many very nice examples that we already know are like this. We already discussed PSL to Z in PSL to R. In fact, there is this famous lattice SLN Z in SLN of R. This quotient SLN of R by SLN of Z is actually the space of just lattices in Rn, lattices in the sense of just Z models spanned by a bunch of linearly independent vectors of full rank. Yeah. So, but this is the space of probably unimodular lattices. Yeah. And you can keep going. You just take any S, I don't know, SP or SON1 or SOPQZ, and it is going to be lattice. Let me now slightly generalize this to the following setting. Let F be a quadratic form. F be a quadratic form. Actually, I can take any quadratic form, just indefinite quadratic form. So indefinite, not degenerate. Generate, so of signature P, Q, and here we have 0, right? This means that I have P positive eigenvalues, right? Negative eigenvalues, and precisely 0, 0 eigenvalues. So I do not have I do not have 0 components in the canonical form of this quadratic form. That's what I mean. So then the group of orthogonal transformations OF, right? Okay, then the group H, which I will denote as O sub F, right? which consists of all matrices in GL P plus Q, such that A transpose F I is F, right? Is a Q group, right?
Oh, we want the form to be.
Yeah, I wanted to say that it's a quadratic form over, it's a rational quadratic form over quadratic form over Q. This is very important. Yeah. Over Q. So this is a Q group. And gamma, which is OFZ, is a lattice in the Lie group. In the Lie group G, which is identified with H of R. And because of this choice of F, this group is precisely S. Okay, it's just precisely OPQ, right? OPQ of R, right? So you're free to choose a form of signature D1 to get something up to commensurability being a hyperbolic lattice, right? And the groups gamma constructed using quadratic forms are called, so, okay, all lattices gamma prime commensurable with OFZ are called arithmetic lattices of simplest type. Lattices of simplest type, or sometimes we will also use the notion type 1, okay? And yeah, that's, I think I can suggest just as a just, well, in fact, let me like write something a bit more specific. Okay, so I can just write F1 be a diagonal form -1, 1, 1. In fact, then, and I can choose another form F2 0, 1, 1, 0, and here's 1. Both have signature to 1. In this case, it turns out that O prime, so I will choose the subgroup of index 2 that preserves the hyperboloid, right? So I will denote as O prime. So then O prime F1 of Z is going to be commensurable with O prime F2 of Z, and they both happen to be commensurable with PSL to Z. In fact, there is the following theorem: any arithmetic lattice in isom H2 non-uniform is commensurable with PSL to Z. In fact, any non-uniform, in fact, any non-uniform arithmetic lattice in isom H2 is commensurable with ESL to Z. So this is this type of examples. All right. In fact, something like, in fact, in dimension 3, there are also such groups that are called Bianchi groups, and they play this kind of role of PSL to Z in higher dimension. Okay, already there we have infinitely many commensurability classes. So here is just one. Okay, yeah, I think let's make a, I don't know, maybe 5-7 minute break, and then we'll continue. Okay. All right, let's continue. So I gave this like first sub-example of series of the general class of arithmetic lattices. But what I wanted to say that, in fact, there is an interesting result due to Winberg about arithmeticity of reflection groups. So Winberg, I will write it as a theorem, which is due to Winberg. In fact, it is proved in his initial paper in 67 on hyperbolic reflection groups. If gamma is a cofinite reflection group, so if gamma in isom HD is a cofinite, which means finite covolume, right? Hyperbolic reflection group, and okay, then it can be arithmetic only if it is of simplest type. So I will say that if gamma is a cofinite reflection group and it is arithmetic, then it is of simplest type. Arithmetic of simplest type. In fact, quite a lot is known about reflection groups in this sense. I will mention probably some state-of-the-art results on the last lecture. Not sure if I will have time today. But in this same paper, Winberg actually proved much more. He suggested, like in practice, quite efficient criterion that allows to verify arithmeticity of such a group. So I will mention this. I will give you this criterion hopefully today. But before doing that, I need to introduce a bit more like number theoretic. Okay, some number theoretic background first, and then I will discuss arithmeticity criterion for reflection groups. This is pretty nice feature of reflection groups that you can really just having a fundamental domain, you can check if it is arithmetic or not. Okay, also, okay, here I actually should say that a surjective morphism should probably be from HR to G, since gamma is not necessarily, I mean, H of Z is not necessarily sitting in HR in the connected component of H of R, right? So generally it can be it may have elements in the sitting not in the connected component. Also, I said that we consider groups without compact factors, but but again, this is just restriction for this case. But if I have a lattice in G times K, okay, let me leave like I want to keep this slide. That's so the definition. This is definition part A, right? For already lattices in non-connected groups, and the definition part B gamma in G prime, which is G product K compact. Arithmetic is arithmetic if the projection, well, it's a maximal compact, right? Maximal normal compact subgroup. Okay, so maximal normal compact subgroup. If T of gamma is arithmetic in what, in just G being the quotient G prime mod K, right? So if I have a product of actually something like that times compact, then I can take the quotient and my image of gamma and the quotient, its projection to the first factor should be an arithmetic lattice. Okay, I will say, so yeah, I said about connected components. So let us move.
Compact factors.
Hmm?
Not dense or something.
Yeah, I think maybe I want it to be irreducible, right? Well, no, in fact, for this, I think, yeah, for this, I don't need it. Yeah, I mean, it can be just like if you just finite number of elements sitting in compacts. Yeah, it's not a problem. In this case, the point is that in this case, the projection is going to be really commensurable with the group itself, right? If it is not dense in K, it is discrete, and thus we have only finitely many elements in K. Okay, so yeah, it's not a problem. All right. Okay, I need to use another check. So yeah, let me move to the left. Yeah, great. So now I want to say the following. In fact, arithmeticity can appear, it may appear using not only the field of rational numbers, it may appear via other algebraic number fields. In some sense, it is not, it doesn't give anything really new, but still, but it would give like arithmetic lattices and be different Lie groups again, and then we will see already this products of G times some compact factors. What I want to describe is the notion of the value restriction of scalars, and then I will give a general statement about yeah. So let me start here. Value restriction of scalars. So let K in K the number fields. Such that K over K is a finite extension. Where D is the degree of this extension. So basically D is kind of like an index of a subfield K in the capital K. Okay, and let X be an algebraic capital K variety, right? Then, okay, so and X K, an algebraic K variety. Then we can see this X, okay, K variety of dimension, say n, right? So how does it work? It works as follows. We view capital K as written in some basis over smaller k, right? So it in fact gives us the correspondence. So I would say that k, right, it can be identified with k to the power of d, right? I would say like as a vector space. Yeah, as a vector space over small k, right? Yeah. So yeah, as a vector space.
Subject to multiplication by.
And right, and thus we can view X as an algebraic variety, which will be denoted as follows. It will be denoted as res sub k slash capital K slash k of X. And this is an algebraic variety already over K of dimension. Do you know what is the dimension? The product, right? It's simply the product of dimension. What was my n times d? Okay. So, yeah, what I wanted also, okay, in fact, this, I would say, stuff is pretty fundamental. I don't know what again to give like too much details about that, but what I want to say is that since we study like Lie groups and algebraic groups, we will be sometimes interested in the real points. So I will probably just mention that the real points of this. So just a remark that the real points of X, okay, of the value distribution of scalars of X, I will denote this. Sometimes it is denoted, okay, when it is so long, we can denote it as sub R, but I will just write R, so real points. They in fact will be, they split into the direct product of the following components. And in fact, these components are, it is just the, okay, I will write, what is it? It is going to be just x of R times x sigma 1 of R and so on times x sigma d minus 1 of R, where okay, where sigma 0 is just the identity embedding and delta J are embeddings of the field no, of the field yeah, I have, so it is precisely what I have D, it is the degree
So-
of,
One embeddings of big K into.
in fact, I want automorphism, Galois automorphisms
Yes,
of,
one embeddings of big K into C. That fix little K.
yeah. Indeed. Yeah,
But see, the product's not gonna be quite correct.
right.
Real and complex.
Oh.
Should behave differently.
In fact, I should write both, yeah. Or C. Well, technically, I can just write C. I will have some bunch of real embeddings and pairs of complex conjugates. Well, okay, in our, I would say in our case, but I can just simply say that these are just Galois automorphisms, right, of the field K over the field, yeah, over the field. Yeah. So let me, where is it? Yeah. So Galois. Morphisms of, sorry, of the, basically of the quotient of the extension, right? K over small k. All right. This, yeah, I think that this is everything that I wanted to use from the restriction of scalars. Actually, I think I will just, okay, I will just write it as the, I think I can just write it as x of, sometimes, okay, I will say the above can be viewed as like the above res k over, sorry, k over k x of R can be viewed as x of, I think x of k tensor product R, right? So, well, I mean, this is just an, this is in some sense just a notation that you can that you can see, but in fact, when we take the tensor, oh, it should be probably capital K over small, right?
Yes.
It should be capital K over small k with coefficients. So this basically means in the sense of, so this is a tensor product. So I take the sums with coefficients from the small k of these guys viewed as vectors over k with R. So it's like, basically it gives me a vector space, right? Real vector space. And if you indeed plug in those elements into X, you will indeed see that it is split into this product. So this is just a notation that you can also see quite often in the literature devoted to arithmetic lattices. All right, so this was a background on Weyl restriction of scalars. What is really important? That there is one-to-one correspondence. So I will probably, I don't know, I will leave it as a theorem. So part one, that k points, right? So that the restriction of scalars, and I will try to write wrong. So the x taken in, so this is an algebraic k variety. So I need to take this k points. It is identified with x of, which is itself a capital K variety. So I need to take its capital K points, right? And the second part, which is also very important for us, that if, so let this O sub, I don't know, K denote the ring of integers. I will just write here L, okay. O sub L denote the ring of integers of the field L. Okay, over field, I didn't pick this field, so over field L. Then I also have the following correspondence. Okay, sorry, I need to write. Then I have the following correspondence: the restriction of scalars of K over small k of X, taking its integer points with respect to this smaller field of the subfield, is also in one-to-one correspondence with integer points of the initial variety with respect to the corresponding number field. All right. So again, just a very standard case where we will use it. This will be some field extension, and the smaller thing will be just a field Q, right? So a typical, for us, a typical application. So our typical application is going to be K is Q over some alpha, definitely of some degree, whose minimal polynomial is of degree D, and small k is Q, just Q, right? So this is going to be our typical application of this machinery. And right, and now what I wanted to say that, in fact, there is the following theorem. So let now, suppose that gamma, suppose that gamma is in a reducible arithmetic lattice in G. Okay, it's in a connected semi-simple Lie group, but I will, yeah, it's semi-simple. So then there exists a number field So an algebraic number field. Okay, I will denote it by L. Part 2. Absolutely almost simple algebraic. Absolutely almost simple algebraic L group. I will denote it by, okay, I do not want to have like too much, but let me denote it by, I know, G tilde, okay? G tilde. And also a continuous surjection. So, and surjection, here the surjective morphism with compact kernel. And okay, I will use, it's from, so it is going to be from the restriction of scalars of L over U of this group G tilde, okay, of R, which is, so what is it? As I just wrote, it is the product by all sigma from L to C, right? And I need to write G tilde sigma of R. And the morphism acts from this product to G, and such that the image of, okay, such that the image of, so if essentially it's the image of G tilde of OL, right? So there is it appears that there is some algebraic group. I'm taking its integer points. Then since L is of some degree over D, then this group of integer points, it's naturally sits in this product, right? Were it just Q, it would be in one component, but since we have some degree, and then this integer points, again, this integer ring looks like a model of degree D over Z, right? So it's naturally sits here, but this is precisely what? This is precisely the image of the, again, of the restriction of scalars over Q of my G tilde, and then applied to, well, basically Z, right? It's just Z. So I'm taking this and take its integer Z points, right? So this is commensurable with gamma, right? So generally, here in this definition, I didn't assume that H, the group H, is simple. You see over here, it's semi-simple. So generally, H itself can be something not really good. Absolutely almost simple. Okay, I do not want to go into details, but absolutely almost simple means that it's really simple, like everywhere. I mean, it's simple even over C, so it doesn't split anywhere. It's okay, its diagram is going to be connected, and so on and so on. So, for instance, which groups are pretty good in this sense. All orthogonal groups of order starting from 5 are absolutely almost simple. All 4, for instance, the group, an algebraic group 031 is not absolutely almost simple, because if you take its complex points, it can be split into the product. There is some sporadic isogeny, but so what is important that you can choose. So basically, this theorem allows you to choose some extension such that an algebraic group defining your arithmetic lattice is absolutely almost simple. So you do not have any non-trivial normal subgroups, right? Well, only what is allowed. It is allowed to have probably yeah, the finite quotients, but so all right. So this in fact, this is going to be in terms of like this definition, one can view it as an equivalent definition, in fact, right? So in terms of this definition, I can actually write something. I will write an example right here. That's okay. So an example, right?
Slide. This, do you know the good like source for this thing?
Source?
Yeah.
Well, this thing is very classical. In fact, I know this is stated in 2 books. Morris' book on introduction, introduction to arithmetic groups. There is also a survey, like a survey book of Winberg, Gorbachev, Schwarzman called Discrete Subgroups of Lie Groups, and this is also there. Yeah, so yeah, this is very classical and this is very important. So what is an example? I think that's a very good example. So an example where I take SL2 of this ring, right? It's ring of integers over square root of 2. So it's going to be a model of rank 2 over z, right? Definitely it can be viewed as a subgroup of SL2R, right? But it's going to be dense, not a discrete subgroup, but it happens to be a lattice in the product SL2R times SL2R. See? So this gives me a simple algebraic group here. So like from this theorem, my L, right, is arithmetic lattice. Arithmetic lattice. So L is Q over root 2, right? Obviously, OL is Z over root 2. And my algebraic group G tilde is just an algebraic group SL2. Yeah. One can do restriction of scalars, right? But once you do the restriction of scalars, you will get a rational group, which is not going to be simple, right? So what it appears. Moreover, you see, we do not have here any compact components. What happens if I can generalize this simplest construction to the case when K is some algebraic number field, and then we will see Okay, yeah, so I should write that this is an equivalent definition, and let me switch the board. In some sense, it is an equivalent definition. I will just use number 3 here. Number 3. So F. Now let F be F is an admissible, I will say an admissible quadratic form. I will just define what it is. An admissible is an admissible quadratic form over some field K. So this means that F is a metric over R just to a diagonal form. So over real coefficients, it is just the form of signature D1, okay? But F sigma is positive definite for every non-identity embedding of the field K into R. To make it very precise, F is the
signature D comma 1,
yeah. So
so no other indefinite form.
yes, of signature G1, yeah. So for instance, it can be like that. Minus square root of 2, 1, 1. The field K is also again q square root of 2. And my sigma 0 identity is just maps root 2 to root 2. And I have only one non-identity that sends square root of 2 to minus square root of 2. Then F sigma obviously is just a diagonal form where I have plus square root of 2, 1, 1, and this is standard positive definite, well, almost standard positive definite quadratic form, right? Then the group of integer points. Okay, so I will take now the subgroup of index 2 that preserves H2, right? In this general case, HD. So O prime of F of OK is an arithmetic lattice also of type 1, where in O prime F of R, which can be identified with isom HD. But let us be more precise what's going on here. In fact, when we consider, in fact, here, I think here we obtain the product of isom HD with the compact. Okay, so let me think carefully about this. So we have an algebraic group, right? And I can take, I will write it this. We observe that for orthogonal groups, the following is true. OF sigma is the same as just OF sigma, yeah? Applying the Galois automorphisms of this group to the coefficient of this quadratic form is the same as applying to polynomials, is the same as applying sigma to all the polynomials defining the orthogonal group. In fact, I should have said that here. Yeah, I didn't really say that in this case. Where was it? Wait, maybe. Yeah, right here. So X with this superindex sigma here means that it is an algebraic variety, right? Whose polynomials being polynomials with coefficients over K, right? But I then apply these Galois automorphisms to these coefficients of those polynomials. So technically, I obtain some new set of polynomials defining already X sigma, and this is a new algebraic variety, right? So X sigma is obtained by applying sigma to polynomials defining X, right? To polynomials defining X. This is the remark that I should have said here on this board. So then coming back to that board with quadratic forms, what I obtain, I have actually two. And then I have the product. So I should take OF, the restriction of scalars, right? I should take the restriction of scalars of K over Q of an algebraic group F, then its real points. It is a product of just OF of R times OF sigma of R. But then this is equal, this is precisely OD1, right, of R. And this is the compact group, OD plus 1 of R. And this is what I obtain in this case. So technically, I get the product of a non-compact group and the compact group. So my integer points. Yeah, so the restriction, right? The restriction of scalars of my, yeah, so basically the image, I have this, in fact, this projection, the kernel of this projection is going to be this, right? The kernel of this projection from this product to G is going to be a compact subgroup. Which compact subgroup? This one. Okay. I hope it's now clear. So yeah. Now, all right. I wanted to say about. I wanted to say something else about the general questions, but Okay, so let me, yeah, apparently we will discuss arithmeticity criterion for reflection groups next time. But I need to say the following very important. I need to give you the following very important result. So now one can ask a very natural question that should immediately be asked once arithmetic lattices are defined. Is every irreducible lattice in G arithmetic? Right, so this should be immediately asked. So it's a very natural question. We know that arithmetic groups are lattices, and we have really a lot of them. So the question, it was known that, so answers in P cell to R, because of deformations, it was known that we can get infinitely many non-arithmetic lattices. So answers in isom H2, we have plenty of non-arithmetic lattices. Okay, I didn't define irreducibility, but like, okay, very roughly, it means that it cannot be decomposed into the product of two lattices, but in fact, the definition is a bit more general. But for instance, if you have a product, it's definitely not an irreducible lattice. Okay, so in isom H2, we have plenty of non-arithmetic lattices because of deformations, right? Because of deformations. Just remember what we did with a pair of pens. You can take any actually reflection group with some, I don't know, with angle pi over 3, and here for, 3 angles pi over 2, and then you can see that there is a connection between the lengths of sides A and B, and you can well, you can work with this. Well, okay, there will be connection, there will be nice connection between the hyperbolic cosine of 2A and the cosine of 2B, and by varying these parameters, you will be able to see that you can get really representations with some very bad traces and elements in PSL to R, right? Okay, so this is just a hint how to get wall. Then, so you notice that this theorem was formulated in around 60s, right? So in fact, it was a bit earlier. It was already known for some large classes of lattices, or of arithmetic lattices, that they are indeed lattices. So there was a conjecture of Selberg and Petevsky-Shapiro that any reducible lattice in a Lie group which is not isogenous to isom H2 is going to be arithmetic. Then Makarov and Winberg constructed first non-arithmetic examples. So this is Makarov in 66, Winberg in 67, non-arithmetic cofinite reflection groups. Reflection groups in isom HD, where D is also 3, 4, 5. And it was like well, it was in some sense a breakthrough in this sense. And in fact, Makarov considered a sequence of triangular prisms in the hyperbolic through space, and was able to show that starting some point, the sequence gives you only non-arithmetic reflection groups, but it was still a prism of finite volume, so it was a lattice. And only later, around, I think it was around 74, Margulis showed that the following superrigidity and arithmeticity theorems are true. And this is a very famous result of Margulis. Around 1974, superrigidity theorem. If G is a semi-simple Lie group, is a semi-simple Lie group of real rank, greater or equal than 2. So in particular, gamma in G is an irreducible lattice. Phi of gamma to G, phi from gamma to G is a homomorphism, is any homomorphism such that the image of gamma, is the Zariski dense in G. Then phi extends to a continuous homomorphism from G to G. This covers the case when you have two lattices. So if you have two lattices, right, gamma 1 and gamma 2, and if you have a homomorphism between two lattices, well, in fact, it can be formulated for different, even for different Lie groups. Then it extends to a continuous homomorphism of the ambient Lie groups. So if you have gamma 1, gamma 2, the lattices, right, then it extends to P from G to G, and these are inclusions as lattices, right? And this is a continuous homomorphism. This in particular implies the most of rigidity theorem in the sense of, yeah, but gamma is an irreducible lattice, and the image is Zariski dense. Yeah, so as I remember, it's even enough to have this image to be Zariski dense. But if it is a lattice, it's certainly Zariski dense. But yeah, if it's a lattice, it is much stronger. So, well, not probably not that much, but it is really stronger. So let me, I think, just move to the right. I'm running a little bit out of time, but so let me just state that this implies this strong most of rigidity, right? If gamma, if G is not isogenous to PSL to R times K, and gamma 1 and gamma 2 are, okay, reducible lattices. Okay, I will say G, J, okay, G with index J. And gamma 1, gamma 2 are reducible lattices in G1 and G2, respectively. Then, so this is comma, right? Then any isomorphism P from gamma 1 to gamma 2 extends to a continuous isomorphism of the ambient Lie groups. This is basically a combination of, well, I mean, you can apply most of rigidity in rank 1, and in higher rank, you apply Margulis superrigidity to the setting when phi is just an isomorphism, but not. So you can take when phi is an isomorphism within this image, right? So this is strong most of rigidity. So then after that, it was like probably a big deal to find some approach to verify arithmeticity. And this is, I think, the first. In fact, there are many results now. And one of the approaches is also due to Margulis commensurator rigidity. Margulis commensurator rigidity. So let gamma be lattice. Gamma be irreducible lattice again. In G. And commensurator of gamma in G is the following group. It is the group of elements in G such that G gamma G inverse is commensurable with gamma. Okay, so well, here I definitely mean commensurable in the standard sense. So then the following dichotomy holds. Then gamma is, and the first part, arithmetic, if and only if the commensurator of gamma is dense in G, and non-arithmetic not its equivalent if and only if, not only when it's not dense, but much better. And this in the non-arithmetic case, the commensurator of gamma is actually a lattice. And in fact, it is a maximal since it definitely contains gamma itself, right? So it is a lattice containing gamma, so it's they should be commensurable, which means that it is a supergroup of finite index, but it definitely is a maximal lattice that may contain gamma, right? So in fact, it is I will write it in parentheses since it can be omitted, a maximal lattice containing gamma. So this means that it is itself discrete nice isometry group. So this is, and this is true always when G is like any semi-simple Lie group. Any semi-simple Lie group. So this holds even in hyperbolic spaces, right? A very nice theorem, and it has also a lot of applications. All right, so okay, so next time, what we will do next time? I will discuss. So basically, now the question is to study arithmetic versus non-arithmetic hyperbolic lattices. I will mention some results in some state of the art, in a broad setting. There are several non-arithmetic constructions. We will discuss them. Probably we will also discuss a little bit different. So I gave you some examples of simplest type arithmetic lattices, but there are more. I will briefly mention what are the other types of arithmetic lattices. I will give you an arithmeticity criterion for reflection groups. Yeah, I think that we will just discuss a few very recent results, also devoted to some geometric approach to arithmeticity. So the question is basically the following: if you have a lattice, how to detect its arithmeticity? And it turns out that recent results allow to detect arithmeticity mainly through geometric properties of the lattice gamma. So I would say, yeah, then next week is canceled, is just to remind you. So the next lecture will be on Tuesday, December 10th. And okay, yeah, stay tuned. Yeah, okay. Thank you.